All right, we are at the top of the hour, so I am going to get us started. Hello, everybody, and welcome to Quantum Analytics webinar. I'm Lauren Armstrong, Marketing Director for Quantum Analytics, and I'll be your moderator for today's event. Today, we're learning all about overcoming challenges in the rapid infrared and Raman analysis of forensic evidence. I'm excited to be joined today by Dr. Tom Tagg, Applications Manager for Bruker Optics, who will be addressing these challenges, showing some real world examples, and highlighting innovative solutions. Dr. Tagg is a member of the Visiting Advisory Committee of the Metropolitan Museum of Art in New York and on the Strategic Advisory Board of Amplified Sciences. He received his PhD from the University of Utah in physical chemistry and a Bachelor of Science in Chemistry from the University of Texas at San Antonio. He is a member of the American Chemical Society for Applied Spectroscopy, American Physical Society, and the Optical Society of America. A quick note about quantum analytics. We specialize in gas chromatography, liquid chromatography, elemental analysis, and molecular spectroscopy-based solutions. Whether you're looking for a single instrument or looking for an entire complete workflow comprised of instruments from different vendors, our team has you covered. Quantum Analytics is proud to be a distribution partner for Bruker Optics, which means that our US-based clients can purchase Bruker's portfolio of infrared, near-infrared, and Raman spectroscopy products directly from Quantum Analytics. As a registered guest, you're going to receive a link to this recorded webinar in your email when it becomes available. We've reserved about an hour for this webinar, including Q&A. Type your questions at any time in the text box in the question module that you see on the right side of the screen. We'll be keeping a roster of the questions and pose them to Tom at the end of the webinar. And to keep things engaging, we're actually going to ask a few polling questions, so get ready to submit your answers. All right, this ends our introduction, so without further delay, I present to you Dr. Tom Tagg. Tom, take it away.
Well, thank you, Lauren. I'm excited to be able to talk with you today about forensics applications of infrared and Raman spectroscopy. It's an area that has evolved and continues to evolve in a very exciting way to provide new types of capabilities for you. Just to let you know, some of the things we're going to be discussing are very new. We introduced the Lumos 2 microscope around this time 2 years ago, which with the 2 years of COVID, seems like yesterday to me anyway. And we received the PitCon Gold Award that year for the best innovative new product. We also are going to discuss Raman spectroscopy and microscopy briefly, and we'll talk about and focus more on analytical tools right in the lab or that can be taken to the field, focusing on the mobile infrared spectrometer we have called the Alpha 2. So without any further delay, let's start talking about forensics evidence by vibrational spectroscopy. So just a few basics. We're looking at providing these solutions, whether it's to customs, police, crime labs, homeland security, wherever you have drugs or trace evidence that you need to have an analysis done. These could be hazardous materials, drugs, and you'll see even when we talk about quantifying things that looking at the amount of fentanyl in a drug-laced product. All of these things need to be characterized. Certainly explosives fits into that category. For trace, looking at small amounts, trace by definition means a small amount, right? So we're looking at fiber, particles, paint chips, or anything that might be found in a crime scene that might be smaller than about 100 microns. We're also going to touch briefly on detecting forgeries or looking at document falsifications and counterfeiting checks and things like that. So Lauren promised a polling question, so we're going to jump right into the first polling question.
Yes, we are. All right, so everyone get ready. We're here for our first poll question. And I'm going to launch it right now. So everyone, what scientific instrumentation do you use in your laboratory? Select one of the following: infrared spectroscopy, DNA, mass spectrometry, gas chromatography, Raman spectroscopy. So yeah, just take a look at that. What's the main one that you use? Kind of give it an answer there. I'm going to give it a second. Looks like the answers are coming in here. All right, I am going to close this out. Some interesting results here. So looks like, Tom, 61% infrared spectroscopy. So it looks like everyone ended up at the right party here. And then followed by Raman, gas chromatography, mass spectrometry, and not a lot of DNA. So kind of some interesting results there. I'm going to pass it right back to you, Tom. Give me 1 second.
Great. Thank you very much, Lauren. These poll questions are really important because it should be noted that about probably 75% of the features that we have in our instrumentation that come in as new features year to year come from our customers. So it's really important to have your feedback. And if you have other suggestions or things that you need to do in the lab that we're not addressing during this presentation or haven't yet in any of our products, please feel free to email Lauren or myself, and we would be happy to take a look at those. Okay, so the next thing to kind of look at, since we're talking about vibrational spectroscopy, is where does it fit into the analytical lab? I really like that polling question because that kind of gives us a good jump off point. So if you look at mass spectrometry, it's a destructive technique. GC also will be destructive, but infrared and Raman are non-destructive, non-altering, and they're very, very highly specific. They're what I call front of the line techniques. So when you're going to use a battery of analysis techniques, it's right at the front. Now, from the polling questions and the results that we just saw, it's clear that you guys are already using infrared and Raman quite frequently in the lab. So I'll go through the next couple of slides a little bit more quickly than I might normally, since we have a very familiar audience here. So we're looking at infrared light, whether generated by Raman or infrared. We're still looking in that fundamental fingerprint region that we call from 400 wave numbers up to 4,000 wave numbers typically. So remember that when we do infrared spectroscopy, we're looking at the interaction of light with molecules. So that's kind of the key. And note that when we take the incident IR light and allow it to impinge on a sample, a couple of things can happen. The light can be reflected, which we're not interested in looking at typically. We do reflection spectroscopy more frequently on trace than we would with an FTIR in general, because with the FTIR analysis, typically we're going to use ATR. The community has kind of gone to that. But for IR microscopy, there are times where you don't want to touch the sample. And in those cases, it would be very desirable to collect a reflectance spectrum, which is certainly done. But for these experiments, we're going to look at the light that is broadband, that is going to impinge on the sample. And then we're going to look at the light that actually gets absorbed. So we're looking at a difference. And in general, we take the instrument function plus the information from your sample and divide it by the instrument function to leave only the absorption spectrum typically of your sample after taking the inverse log. Okay, so this is a good pictorial example of light passing through water. Some of the light actually gets coupled to the vibrational modes of water. We have the symmetric and anti-symmetric modes, stretching modes for water, and the deformation. Just a very discrete technique. So even though water, it would seem, could have many modes of vibration, intuitively speaking, there are only 3 allowed vibrations here. And as it turns out, even the rotational energy levels of water are very specific and finite. And as it turns out, when you look at water as a contaminant to a normal infrared spectrum being collected, it's a very strong interferent. And so you have to be careful to minimize water in your data, as it is a strong absorber. Okay, so this is what the spectrum looks like of water. And you'll notice, well, these bands are really broad when I look at the stretching bands off to the left and the bending band off to the right. That has to do with intermolecular interactions. So for vibrational spectroscopy in the minimal infrared region of the electromagnetic spectrum, we're normally looking at essentially intramolecular vibrations, but these molecules can interact together. And so we see, because water is obviously such a strong hydrogen bonding molecule, these bands are badly broadened. Now, I mentioned ATR, attenuated total reflection. So this is the method that we'll almost always use when we're using a portable FTIR to do the analysis quick and easy. Why? Well, you don't have to really worry about a purge, for example, or water, because the system is typically sealed with the ATR crystal on the top. The beam comes from the bottom, as shown in this pictorial representation on the left. It bounces off the ATR crystal sample interface. A standing wave is generated that brings information back from the sample and goes to the detector to be detected. So it is a very efficient technique. You don't have to worry about saturating the signal like you would have to normally worry about in transmission. It works for virtually all sample types, liquids and solids, very, very well. Again, the depth of penetration is only a couple of microns. So again, you really don't have to worry about doing dilutions or anything of that sort. And it's independent of the substrate material. And you can do this technique not only macroscopically, but it's very commonly used for IR microscopes as well. So what can you analyze, pragmatically speaking, by doing a simple ATR data collection? So it works great on pharmaceutical products and drugs, caffeine, benzocaine, ketamine, cocaine hydrochloride. Virtually any molecule that has covalent bonds will work really well. So certainly pharmaceuticals and drugs, organics and inorganics, where you can see talc, calcium carbonate, polyethylene glycol, mannitol. And for polymers, polymers work extremely well also. So you have 4 really good examples there. You can see that the bands are really typically sharp, well-defined. This is why infrared and Raman spectroscopy are such valuable techniques, is that each molecule has its own fingerprint signature, so to speak, in the middle infrared region of the electromagnetic spectrum. So you can almost always get a good identification of an unknown. And so that's the goal, right? So there are 2 types of samples we're looking at. We want to verify a known, which certainly happens, and we'll discuss that as we go along a little bit. But we also want to identify unknowns, and this is where the true value is for infrared spectroscopy. So we will compare to a database typically, so we'll search the database. It's important to note that the quality of the spectrometer is important in these types of analysis. Well, why? Well, as it turns out, wavelength position is actually the most important criterion used for a library search over a database. So if the instrument is not really accurate on the x-axis, then you don't do so well when you do the search over databases. And identifying unknowns. So what the software will again do at first is say, okay, what do I have by these band positions? This is a CH stretching region here at around 3,000 wave numbers. We have a carbonyl band and such. And then when you look at the library search, you can see I have a nearly perfect match with ethyl formate. So these libraries are immensely useful. What I normally recommend for people in an industrial environment is actually to collect data from samples that they might have as an interferent or such. In this case, we're doing a forensics investigation, so it is really important for you to have good databases of fibers, drugs, or any other type of sample or evidence that you might need to perform an analysis of. And because you might need to testify in court, it's important that these reference databases be validated. So creating your own databases can work, but you usually will have to use a third party to validate the data collection and the archival, which is a step that most all forensics labs are really not interested in doing. So using validated databases is really important. Okay, so I mentioned one of the really important applications of infrared spectroscopy is actually doing quantifications. And we have seen a huge increase in our market for selling alpha FTIR systems for quantifying fentanyl in drugs. Why? Obviously. So we've sold these to clinics and outreach centers where people are able to analyze drugs that a user might bring in to make sure they're not going to have an overdose. And so we can actually quantify on that and let them know reliably that, yeah, you're probably okay. It's a little bit sad when we look at the number of people that are suffering from fentanyl addictions. In the United States last year, I believe the number was over 100,000 people died from fentanyl overdose. So about 20,000 in Canada. So this is really an important capability in the alpha system to be able to do those types of quantifications to help users try and avoid overdosing. It can also be used for virtually any system that you can present a calibration sample set. So if you say, I'm going to develop, I'm interested in quantifying X drug in whatever, you present known sample quantities, the software will very expertly take you through the wizard to develop the model, and then you have that reference calibration set to be able to predict the unknowns. Other types of applications, looking at drugs, explosives, and hazards. So in that case, we're looking at a bulk material. One of my favorite tricks for that type of analysis is actually to use a little bit of sandpaper, and you can take the background from the sandpaper and the sample acquisition from the actual the material that has been caught on the sandpaper, and just works great. A non-obvious way to look at trace materials from very large objects. Again, fibers, particles, paint chips, varnish, tapes, and such. Tapes are particular interest and becoming more important for the analysis in a forensics lab. Falsification of documents, art forgery, and counterfeit money, they've become more prevalent. And as you can see from this image below, that's a Tonka mural. Certainly, authenticating art objects is really important, and I've been involved with quite a few of those, as you can imagine, being on the visiting committee at the Met in New York. Okay, so identification of suspect bulk materials, drugs, and legal highs. So again, this is a front of the line technique. So why? Because it's non-destructive and is the most discriminating. So mass spectrometry, NMR, Raman, X-ray diffractometry work well, but I would probably bump Raman up a little bit in that hierarchy. But for infrared spectroscopy, it really has been shown to be the best tool for doing this type of looking at drugs and legal highs. So looking at heroin, cocaine, amphetamines. One of the things that I wasn't aware until I started preparing for this is there are many over-the-counter products that are used for what are called legal highs, things that are derivatives of common drugs or things that people are woofing or whatever, and or huffing, sorry, and so-called research chemicals, plant foods, banned. Other things that are banned now that weren't previously, bath salt drugs, many other things, and unfortunately, as the law enforcement becomes privy to these types of things, and some products would be altered or regulated, like Sudafed was years ago, that community is very agile in coming up with new ways to get high. So we look at this rapidly changing market. You can see new psychedelic drugs here year by year. Just 10 to 15 years ago, the number was pretty non-existent, right? There were only 5 to 10 of these new drugs a year, and you can probably keep track of that. But as you can see, by 2014, more than 100 new psychoactive drugs have been identified by the EU. In the US, that number is even more remarkable. And you can see literally hundreds of new drugs coming into the community year by year that people are using. So how do you keep up with that? Well, the answer is you want to use active databases to be able to, and by active I mean those that are updated on a regular basis. And again, you can also create your own databases. So with that, let's go to our second polling question. Over to you, Lauren.
Fantastic. Really great stuff here. I'm kind of intrigued to see what the answers to this next question are going to be. So next up, I'm going to launch this poll. What area of forensic science would most benefit from a technical breakthrough? Really interesting question here. So think about it. Those in the forensic sciences that have been doing this for a while, like what area is you're kind of most interested in seeing a technical breakthrough? I'm going to give this a little bit more time. Looks like we still have some answers coming in. Oh boy, yeah, a lot of people are interested in answering this. All right, here we go. I'm going to close the poll and share the results here. Wow. Not sure, Tom, if you see any surprises here, but trace evidence looks like that's the winner, but not by a majority. Hazardous materials at 23%, legal drugs 20%, and counterfeits and forgeries at 13. So looks like everyone's interested in a little bit of something, but definitely trace evidence looks like it's the winner there.
Well, that's very interesting. Maybe a little bit unexpected. I'm surprised that counterfeits and forgeries came up that high. So we appreciate your feedback there, and we'll take that back to the development team. Okay, so substance identification, where and who. So you're going to be doing this work in the forensics lab. There are chemistry labs sometimes as well. In the image on the right, you'll see Professor Fiona Measham in the UK testing a drug sample at a nightclub. So many times people do end up going out to nightclubs, festivals, and such, trying to identify problems before there are injuries there. The users typically is law enforcement and customs officials, particularly in the US. Scientists and laboratory staff usually will not be involved in the field as much. That would be back at the lab. Again, one of the requirements there that when we develop the software for doing this type of analysis is it really needs to be easy to use, easy to transport, just brain dead easy to run. As I mentioned before, we have these systems in outreach labs. These are not scientists running these systems the majority of the time now, I would say, in a forensics world, by encompassing outreach places and such. I'd say that more than half the people doing forensics analysis with our alpha systems are not science people at all. So that led us to actually, when we realized this from polling questions several years ago, we wanted to develop an interface that actually would meet those requirements. And so we developed what we call Opus Touch. And so now you can see the spectrometer on the left, and it has the ATR crystal. I'm highlighting with my pointer. You can, if it's a large object, you can actually bring this little plunger down to make contact and pin the sample to make good contact. If you're doing identification or verification, you have both of those available. You can see you will get a check mark in the software. And we have what I mentioned is an active database. So we have the compliant TIC-TAC database for drug identification, and this is regularly updated, and it has to be updated actually annually as these new types of drugs come in there. And you can see that, wow, we're up to over 26,000 entries in this database, which tells you how active that area of research really is and development. So again, we're doing either an identification of an unknown typically, or quantification in the case of fentanyl. As I mentioned, it's applicable to pretty much any sample, less than a minute, and gives you very reproducible and reliable results. I would say ATR infrared spectroscopy is as reliable as it can get. And it's actually very, after an initial outlay, it's a very low cost way to do a very careful and reliable scientific investigation, really. So, and again, this is certified. The system also tests itself. It has an OQ and a PQ. One of the advantages of a company like Bruker that sells into the pharmaceutical communities and many systems into the forensics community is that we know we know your world, a regulated world, and how to provide instrumentation that it runs itself, doesn't need user intervention, and prints out either digitally and or hard print these certificates of OQ and PQ to include in your SOPs. So how much sample do you need? Typically, we're talking about milligrams. So the sample analysis area is about 1.5 millimeters on square. So about a milligram. You can do smaller amounts of material, so you wouldn't cover all the crystal down to something you can see, which is about 100 microns. And in that case, you're looking at microgram quantities. And it's, as you can see from the gentleman carrying the instrument on the right, it's not heavy, and but is extremely robust. We actually had a new type of source that we introduced to our infrared product line called the center glow source. It has a much higher photon flux than previous sources. Virtually all the light from the glow bar is used. So this improvement means better signal to noise than even previous alphas would be able to achieve, which is really the market leader in signal to noise. The interferometer is rock solid. We have a patent on this interferometer design, so it's extremely robust and trouble-free. And we use a diode laser, so you can see the mean time between failure of anything would just be this source, which is only a few $100s to replace. So it's expected that this system will last a very long time, by at least 1 decade. And we certainly hope longer than that. And you would expect not to have to spend more than again, a couple of $100s on a new source, somewhere between 5 and 10 years out. Another point to mention that's not a small point really from a user perspective is that we actually elevate the temperature inside that little spectrometer a little bit to provide even more stability. Why? This actually allows us to strip off any water vapor that might be in the spectrometer to ratio off extremely efficiently. So it's very, very rare that you would see any contamination from water vapor in any of the spectra collected with the alpha. Now, this is the workflow I mentioned. So when you first go in, you can do an analysis, identification, verification, or you can pull up spectra that you've seen before. If you want to change parameters, you can click on advanced. I would like to point out also that on the upper left, the person that's logged in is an administrator. So even though this GUI or graphical user interface is simple already, it can be simplified even further in restricting access, say, to an operator, that they would log in, it would show their name or whatever there, and then they might, if they're only supposed to be doing identifications, they'll only see that icon and can't click on anything else. So this very nice workflow allows the lab manager really to set things up the way they need to be. Again, keeping it very simple. So what's the workflow? Well, you collect the background, you collect the sample, and then automatic library search is done. And you collect the background, and then you type in the name of the sample that you want to type in. You get a preview scan on the bottom, so then you can see exactly what you're doing. There's the scan, and now the total acquisition time, again, as you can see, is very quick. So it's 1, 2, 3, 4 seconds for the scan, and then the spectrum search is being conducted. And again, this is over 26,000 spectra. And the report is generated, and you have it digitally or hard print right there. So it doesn't get any easier than that. Compact dimensions, again, this is the size of a textbook, maybe a stack of 3 or 4 textbooks. I like to take it in this little case wherever I go. It's not heavy, less than 15, about 15 pounds. It seemed a little lighter than that to me. You don't have to worry about bringing a PC or anything because it's the computer built on the spectrometer. The Tic-Tac library, I mentioned that before. This was released by Tic-Tac Communications in the UK. And so it allows you to identify new drugs, new psychoactive drugs are added on a periodic basis. And again, that's critical for getting it right. There's a list of some of the new drugs that have been added over time. And again, we use certified reference standards to make sure that everything, that these compounds that are going into this database are accurate. And again, library searching, here's a good example of cocaine hydrochloride, and here's methadone. Again, you can see the perfect match. You can see the hit quality is very high for these. Sometimes there's more than one chemical in the drug, and the software works very well for a mixture analysis as well. And this is a really fine result where you can see you have phenacetin, benzocaine, and cocaine. Show all the composite spectrum shown there, and you can see the residual showing that essentially we've identified everything in there. Again, quick and easy to do in the software. You can also do propellants. So here are 3 ATR spectra collected, one on Hodgkin's smokeless rifle. You also have accurate arms number 5 and Hodgkin 777. So again, very high quality data collected in just a few seconds by ATR. You can do explosives. Bruker Scientific sells a product called the detector. And so this works very well by ion mobility spectrometry. You can see again the identification quick and easy in the Opus software to do the identification for the plastic explosive. And quick and accurate, and all on the same platform, which is very nice again, using the software that is readily available. Again, where does FTIR fit in for doing trace analysis? So you know, you can try and do fingerprint analysis, DNA analysis, metals and alloys, XRD. You can use XRF and such for metals. But the best thing to use for specificity is essentially still infrared microspectroscopy or Raman microspectroscopy. So a good example of that is looking at tape, right? So sometimes trace evidence follows microscopic analyses. Tapes are used to wrap drugs or bomb packages. There are a lot of different tapes out there. So this is a really good opportunity when you're doing a forensics analysis to really lock in on evidence that might have been found in possession by a suspect. So again, the tape is best done just by the alpha 2, and when it's smaller, you might need to use microanalysis again for particles, fibers, multi-layer paint chips and such. So again, this is a simple tape analysis, allows the accurate match of a tape found at a suspect. I'm preaching to the choir a little bit, but we all know that you're not necessarily going to say, okay, you know, I'm going to find a car that was in an accident somewhere in the United States, but when you have a suspect and that you want to verify or eliminate that particular suspect having been at the crime scene by, say, by leaving paint on a suspect that was in a hit and run or in another car. So you're using it as confirmation analysis. And so this type of tape analysis, again, is really important. You can see the PVC tape result, acetate tape, and polypropylene tape. Very, very different. And again, there are many different types of tapes out there. So this is a really fine way to confirm or add more evidence to the body of evidence in looking to bring a case against a suspect. So when we're looking small, now we're actually looking at nanograms and picograms. We're looking at things that are about a micron or so to a few to several microns. Raman microscopy works really well for getting a little smaller. Raman microscopy can also do confocal depth resolution. Raman microscopy in non-depth profile mode, it usually penetrates just a few microns depending on the type of sample that you're working with. If with FTIR, it can penetrate anywhere from just on the surface only, if the sample is about 10% reflected or more, down to 10 or 20 microns for doing diffuse reflection. Again, we're doing transmission, reflection, or ATR. And again, ATR is the method of choice again, because you get transmission-like results without having to worry about path length, and it's quick and easy. So the best way to do this is what we call this ATR approach, where we have a vertical engagement of the crystal. We have the pressure sensor built in, so you can select the contact pressure that's desired with the sample and the deceleration rate in making contact with your sample. So some samples may be a little more fragile than others, and so you can actually change that again quickly and easily in the software. So this is the Lumos 2 I mentioned before. So it's we had the video wizard for guiding you through the acquisition and the processing as well. So everything is under computer control. It has the highest performance. I mentioned the center glow source that we use, as well as this short beam path you see here. So unrivaled performance. And you don't need to have any widgets or knobs or anything you have to learn. This system, literally, if you were going to come visit my lab, I might run one sample and then I'd turn everything over to you, and you would literally be able to collect very high quality data right away. And as with the alpha, this is meant to be absolutely fully reliable for many years. And as we talked about with the alpha, the same thing is true for our infrared and Raman product line. So they automatically will test themselves. You generate the OQ and the PQ, and we actually like the configuration for the Lumos 2 that has the zinc selenide optics. So it's sealed. You don't need to worry about potentially damaging water-sensitive optics, and because the beam path is short and everything is tight inside there, it's rare that anybody even needs to purge the Lumos. And as you can see, very long expected lifetime, as with the Alpha 2. I mentioned how the ATR crystal comes down, so you can see on the left. You can also see the long working distance, so you can actually place a sample that's more than an inch thick under the stage and still be able to get down and do a good analysis of it. So you can analyze small objects or small parts of small evidence or large objects. There's enough room on the stage to accommodate very large objects. And again, you're going to go through the video assisted measurement. You can measure the sample, you can annotate the sample, and you can also, as you can see on the right here, the crystal comes down and you have 3 contact pressures. So the contact pressure is just automatically and very reproducibly made. It allows you to do quantitative ATR really for the first time with the Lumos platform. Now, one of the nice things I like about the Wizard is that it's just dead easy to use. So say you have 10 paint chips you want to analyze. You can actually just put 10 paint chips on there and draw 10 area maps, or 10, which I like. So I can say, I'll put 10 samples I want to analyze, go away to lunch or for 30 minutes and come back, and I'll have all 10 of them analyzed. So it's a very easy to use platform. And as you can see from the Wizard, you can actually define point maps, line maps, or area maps quickly and easily. So here's a quick example where we're going to look at 5 fibers here. You can see them. It's easier when we pin them down with this match, so you can see the 5 of them. You certainly will want to use polarized light, which is very handy for looking at fibers. And so this is a good example where we use polarized light on the image. And then now we just quickly and accurately go ahead and collect the 5 ATR spectra collected from each of those fibers and do the identifications using the ATR complete database. We also have synthetic and natural fiber databases. Here's another good example where we're looking at talc. And so we have cellulose on the right and talc. And then you can also look at forgeries and such. So I think once we embed our paint chip in a methacrylate medium, typically, you can put it into the microvise shown on the right and do the analysis. Here you can draw the aperture to whatever size you want to form perfectly for each layer. And as before, the analysis is quick and easy, and you can actually do mixture analysis on these types of samples just as easily as a single component analysis. For forgery, again, this is really an interesting area of analysis where we're detecting falsification of documents, looking at an art object that someone may have tried to pass as an authentic. Many modern artists have been people try and copy. Jackson Pollock is one example where there are many people trying to, it seems like, out there trying to copy the work that he did. And counterfeiting money has obvious merit if you can get away with it. So here's a good example where we're going to do look at an 8, and as it turns out, when we did a quick ATR map, you can see that a different ball pen was used. So just doing a quick image, you can verify that there were 2 different inks used there. looking at fingerprints so that you can do a fast image. So each one of these squares is 1,000 spectra. So there are a lot of spectra here. We have applications like with microplastics and others where we will collect several million spectra quickly with the system. So you do have those capabilities. So for latent fingerprint analysis, I think this is maybe the first time that you can say that that becomes practical to image over a large enough area, like an inch by an inch. That's a trivial size, really, for doing the analysis with a Lumos 2 or a Hyperion 2 microscope that we offer. And then when we look at the spectra, there's the protein, salt, and ester. Bruker just this last month introduced a new infrared microscope. It's a little bit specialized for some applications, but I do want to make you aware of it. We use an optional quantum cascade laser device to actually do the analysis. So we can actually do, as you can see, 6.4 millimeters per second. So that's essentially 2.5 by 2 millimeters square with 5 micron precision in 1 second. So this system is very new to the market and has very novel capabilities that no one else has even thought about doing. Now, I mentioned those paint chips, that while they can be done pretty fast on the Lumos 2, on the Hyperion 2, you can now literally image across everything in just a couple of minutes and get very, very high quality data. And as you can see in this example, only the FTIR spectrum can be used to identify the antimony oxide that was there, the flame retardant. And then when you look, what to use Raman for? Raman works tremendously well for pigments, for media. When you're looking at paint, IR works really well for media, not as well for pigments, because pigments tend to be inorganic many times. Maybe reds might fall into that category where you have more organics used more recently. But in any case, if you're going to forge a painting, many times people are trying to go ancient, and again, those are better. Those are usually ferric based. And Raman, you can actually do really nice depth profiling as well as getting those inorganics. And for me, they work great. Remember that the infrared spectroscopy is working to collect data efficiently on anti-symmetric modes of vibration and Raman symmetric modes of vibration. So I saw from the poll that many of you probably have both of these tools in your lab, and that's the way to do it. The Alpha has its companion, the Bravo, for doing mobile Raman analysis, as the Lumos 2 has its counterpart, the Centera 2, for doing the Raman microanalysis. And so again, the same video wizard, you don't need to learn new software. Everything is calibrated with the system. Every spectrum you collect will be calibrated. You don't need to place any samples on the stage to calibrate the systems when switching between lasers. You can do fast imaging there. So this is a full featured Raman microscope system. This is one of my favorite implementations of the Centera. This is actually looking at a Tonka mural. This is from Richard Ernst's private collection. Again, we can place that work of art on the stage, and we can actually map it very nicely. It is still under software control. The stage can be mounted underneath that large stage. And this was an ink crossing that I thought is also very interesting to look at. So I have the Z grip and the ball pen, and which was done first. So we'll just map that corner shown here in the lower part of this right image. And these are the raw spectra. And so you can see the top is the Z grip and the bottom is the ball pen. And it's hard to even see any bands in the ball pen. And once I use the Bruker's patented concave baseline correction, I can strip off the fluorescence and actually get a really, really fine result in being able to differentiate. When you look between around 1200 and 1700, you can see very many differences. And then when we look at the distribution, we can see the paper as shown here on the right, the cellulose band, but we can see the 1637 band and the 1146 band due to the two different inks. Very nice in depth to see the top ink, the ball grip being on top down into the paper. And then when we look at the Tonka mural, you can see that we need 2 different lasers to do an ideal analysis. So for cinnabar and orpiment, it's best to analyze at 785. For cupric and ferric based and even 3D transition metal based compounds, it's better to work at 532 whenever possible. And another fine example, again, that might not be obvious is actually looking at RDX and other propellants, and you can collect really fine spectra from these. I usually use a hydrophobic substrate to dry them, so you can see they get concentrated here on the perimeter as you dry them onto the slide. And this type of acquisition can be done in literally a couple of seconds. So kind of summarizing some of the benefits of infrared and Raman spectroscopy, these systems have become really easy to use. It doesn't matter whether you want to perform the most complex Raman or IR microanalysis or a verification of a drug. The software is just immensely easy to use. You can sit down, you could take this home to your middle schooler and they can collect data quickly and easily. We really have reached that target, I think, right on. The systems are very reliable and reproducible, and then little to no sample preparation required, universally applicable to solids, liquids, pastes, colloids, so forth. Very short acquisition times. The Bruker has really improved the signal to noise performance on all of our systems, but with the new center glow source, it's even more so. For example, you can imagine collecting 6 million spectra for doing a microplastics identification or fingerprint analysis. That it has to be fast to be able to do that type of analysis. So we've gotten there, and there's no consumables, so there's no waste, and again, it's very safe. And at this time, we'll open it up for any questions you may have, and thank you for your attendance.
Fantastic, Tom. My goodness, I always love it when there's a topic like forensics it's really interesting, and it helps really describe how these products work. So I know I took away a lot. Thank you so much. And for sure, we have a ton of questions. So if you have questions for Dr. Tag on this topic, any of the instruments that you've seen, and any other information he shared today, please type your questions in the question module that you see in the GoToWebinar control panel. Um, while I give some folks some time to submit the questions, I just wanted to give a couple plugs for some upcoming webinars that we're having. On March 16th, we're going to do another webinar on taking your GC analysis further with innovative GC FID solutions. This is going to be a webinar presented by Quantum's new partner, Activated Research Company. So join us for that if that's something you're interested in. And on April 6th, we have another webinar on gas analysis in real time by mass spectrometry. So lots of good education coming, and I know this is never our last webinar with Tom, so you will hear more from him at an upcoming webinar. But with that being said, let's dive into this Q&A. Tom, first up, can fentanyl be accurately identified by FTIR?
Yeah, so I alluded to that. Not only can it be identified, but it can be quantified, which is again, it's a tragic situation to see, what's happening to many families in America with fentanyl addictions. But yeah, this is maybe the most important implementation Bruker's made over the last few years for the forensics community for saving lives, is the ability for these outreach centers to identify and quantify the fentanyl to let the user know whether they can consume it safely.
Fantastic. And I think there was just a really quick clarifying question. What is mannitol? I think you had it on slide 11. I believe that's a sugar, right?
Yeah, that's right.
Awesome. And the next question is, can Raman analysis distinguish between various black pigments?
So black pigments are pretty much exclusively done best by Raman, actually at 532. So you can differentiate carbon black from bone black. We use this Raman for this very routinely when we look at ancient art objects. And so yes, you pretty much, if you're going to do carbon and you want to identify the black, well, you need to do Raman at 532.
Awesome. We actually got a couple questions about the libraries that you talked about for the
Yep.
materials and compounds.
Yep.
How are they available? Do you purchase them as a subscription? Like, how does that all work?
So you can subscribe to them or you can buy them. And a lot of it, in my opinion, depends on your use. If you're just going to run them once in a while, you don't need to spend a lot of money on a lot of libraries. So you can pay a small amount to subscribe, and only if you find something useful will you actually go ahead and pay the price for it. But these databases are coming down, so that ATR Complete Library has a lot of sample data in there that would be useful in a forensics environment, and they're not very expensive. So again, it would depend on you.
Fantastic. Um, this is a question kind of about ATR. In the case of hydrophobic um, compounds, ATR might not be the correct choice, or do you have any suggestions for that?
No, ATR is ideal for that because all you're just going to do is just drop it right in the center and it'll stay there. If you feel that it's running off because your lab bench is not flat or anything else, you can just put a little ring there, a little gasket, and the liquid won't run off. So the hydrophobic, actually for liquids, that crystal is meant and designed to be hydrophobic. So hydrophobic materials work ideally.
Fantastic. Couple interesting questions about liability issues. And I don't know if you get a lot of questions about this, Tom. What sort of liability issues arise when if the system identifies it incorrectly? Do you certify the identifications? Um, how do you answer questions like that?
Usually that responsibility falls to the analytical lab. So you have to be very careful to use libraries that have been validated by the right law enforcement people, like the Tic Tac library has been. So yeah, the ultimate liability will fall, as it always has, to the forensics lab.
Awesome. Um, can the can FTIR identify drugs within the same family, such as compounds of diazepines and different compounds within amphetamines?
Yeah, absolutely. Again, specificity is the greatest tool for this benefit. If you find that you need to look at polymorphs more carefully, it may be that they differ only in solid state modes, which is the far infrared region. And we do offer an option. It's called the FM. It's the far mid. So you collect an ATR spectrum that gives you both ranges simultaneously, and that really gets at it really well, where you're getting the far and mid in one acquisition, and even very small differences like nylon 6,6 being formed in one temperature versus another temperature a few degrees hotter or colder. You'll see changes down in that solid state region. So that's a great question.
Awesome. I got a couple cool questions for you here, Tom. Number one, when will Bruker combine IR and Raman in one instrument?
So the answer is as soon as the laws of physics change. So, so, so with Raman, because the scattering efficiency is much better at the shorter wavelengths, you must work in the visible if possible. Unfortunately, the same optics that work great for transmitting light in the visible are opaque in the mid-infrared. So you must make some horrific compromise to do one or the other in the other's home on the other's home court, so to speak. So we've continued to follow the policy for all of our instrument lines company-wide that performance is king. So we would rather not make those kind of sacrifices. You can get something that would be really mediocre in both, or you can get a Bruker system that will be ideal in performance with both.
So I guess we're not going to influence Bruker R&D on this webinar. That's fine.
No,
That's
not that one.
fine.
That one we've looked at for decades, and so that's a great question, but one that we still that's making compromises we don't feel comfortable with yet.
Well, Tom, you'll let us know when you in physics change your mind on that. But moving along, can Raman be used to identify controlled substances through packaging?
Yeah, absolutely. So my favorite way to analyze those is actually you can use the Bravo handheld or the Centera 2 Raman microscope, and you just look through the packaging. And in the confocal mode on the microscope, you won't even see the packaging. You only get the drug inside. And in fact, it is so good. I have one of my favorite examples I use in a more detailed Raman microscopy lecture is where we look through packaging material and through the syringe wall and through some fluid in the syringe to identify the particle inside. So that you can really do very, very fine work, not only looking through packaging, but other thick material as well. So Raman is very well suited and maybe ideally suited for analyzing things inside of packaging. So if you find drugs at a crime scene, you just throw that in, whether it's in a suspect's toilet, which it seems that's where people throw them, and you throw it in a chain of custody bag, and now you have 2 bags to look through. You just take that back to the lab. You go ahead and put it on the stage of the microscope, and you can look through there to see exactly what you're looking for. And you never have to break the chain of custody.
Awesome. A question here about detection limits. What is your detection limit of it? It doesn't specify the instrument, but I'll just ask the question. What is your detection limit of a hazardous or toxic material buried within a matrix substance, like say 1% cocaine in mannitol?
Yeah. So if you look at what the detection limits by IR and by Raman, Raman is limited to about 1%. It's very hard without using some enhanced technique to get better than that. IR is much better than that. So you would 1% would be right at the limit for Raman and would be pretty darn easy by IR.
Awesome. And this is a question
Well,
about the Lumos.
maybe I'll
Oh,
add to
sorry.
that for
Yeah,
just a second.
go for it.
It's sorry to do that to you, but if you look at improving your detection limits, you want to use a quant model. So you can go between 10 and 100 times better in detection limits by developing a quant model, and you'll pick things up really, really well. We have customers that are using the Alpha 2 to get certainly down to 100 ppm by using quant models. So that's another thing to consider in a forensics world that might be worth your trouble to if you're seeing a certain type of problem in your jurisdiction, it's worth it to develop a model. And we have good expertise at Bruker to be able to provide assistance in helping you to do that.
Awesome. This is a question about the Lumos 2. Can you recap? Is this a research grade and really should only be used by trained professional technicians? Can you remind us on that?
Actually, it's a research grade microscope that my young grandchildren can run fine. So
Oh,
it's
wow.
it's that easy to run. All you do is you have a mouse-driven software that you use the video wizard. I jokingly call him Gandalf the Grey. He's a gray icon in the software you click on, and you can't get lost. If you're not sure of something, you click back in the wizard. If you're ready for the next screen, you go next, and then so it doesn't get any easier than you being able to use these simple video guided measurements for state-of-the-art infrared and Raman data acquisitions. And it doesn't matter, even if you spend top dollar on the QCL based microscope, it's still using the video wizard. So all of our IR and Raman microscopes use the video wizard.
Awesome. Talk a little bit about the OQPQ validation. What does that look like?
So it looks like whatever you want it to look like. So these systems are intended to fit right into your SOP. So when the engineer or the salesperson, depending on which instrument you get, comes into your lab, you tell them how often you want to do the PQ and the OQ. Usually people run the OQ semi-annually or annually and the PQ daily or weekly. And it's easy to set up in the software. You just log in as the administrator. You change those things. In a regulated environment, it'll need to be countersigned, and then away you go. So it's that easy to implement really what we call the OVP program into your SOP.
Awesome. A couple questions here left. What would the application for fingerprint analysis by FTIR be associated with?
Well, it depends on what you figure the suspect has been up to. So you can look for explosives and precursors that have the compounds embedded in the fingerprints. They could be messing with drugs, so they might have cocaine or fentanyl particles stuck into the folds of the fingerprints. Washing your hands will not get rid of it that easily, so you can actually just you can roll a PVDF membrane or something over the fingerprint and be able to do the analysis quick and easily that way. So yeah, you just whatever evidence is on the fingerprint is what you would do the analysis for.
Awesome. And this is kind of a cool question to end it on. What degree do you need to go into this field? And what degrees do you have, Tom?
Well, you don't really need a degree but in general, people end up with a chemistry or forensic science degree or both. I have a bachelor's in chemistry, as said before, a PhD in physical chemistry, and I also worked as a medical technologist before that. So I've you know, spent some time listening to lectures. So
Sometimes that's all it takes, right? Is a little bit of experience combined with the right background. Awesome.
yeah,
That brings, oh wow, look at this is perfect. It brings us right to the top of the hour, just on time. Thank you so much, Tom, for presenting today's webinar. Everyone who registered, for those who are listening to this on demand, you're going to get the link to this in a recording once it's available. That is it for us. So we'll be in touch with everyone. Hope everyone has a great day. We look forward to helping you expand the boundaries of your analysis. Take care, everybody.
bye bye.
Bye.